Hey Calculus, this is Mr. Florio. Today's going to be a special day. 5.4, the fundamental theorem of calculus, one of the few words in the dictionary that have three letters capitalized. And this is going to be a big deal. A lot of maths have like the fundamental theorem of like algebra, the fundamental theorem of other whatever subject it is, but the fundamental theorem of calculus is a big one. And we're going to relate the two things we've kind of done in this chapter. We've done indefinite integrals. So if I said, if I have the function x plus x squared, the antiderivative of that would be like 1/2 x squared plus 1/3 x cubed plus some constant. And how does that relate to this thing, the area between your function, the lines a and b, and the x-axis? Um, this was like, we said you could also take this as like the limit of a sum. So you take a bunch of rectangles, and then the width of each rectangle approaches 0. That was the norm. You could think of it as the n approaches infinity. And we took the limit of the sum from one rectangle to n rectangles of f of ci delta x. And somehow there's a relationship between these two things. And that's what the fundamental theorem of calculus is. So what is that relationship? There it is. The fundamental theorem of calculus, you definitely going to want to write this down. It seems pretty small because you're not writing a lot, but in short, if we call capital F the antiderivative of little f, then if I want to find the definite integral of a function from a to b, how does that relate to the indefinite integral? And you find the antiderivative, and you just plug in your limits b and a and subtract them. So this is a big formula. It's a little different from most formulas where you think just plug in numbers. You are plugging in numbers, but you also have to do some calculus with them. So the first video, I'm just gonna do some examples, and in the second video, we'll do a couple other things. But now we just need to use that formula. So we need to evaluate these definite integrals and the fundamental theorem of calculus. If I want the antiderivative of my function from a to b, we just find the antiderivatives and plug in a and b. So this is going to be a big deal. Just like you took derivatives, evaluating definite integrals is going to be a big thing. So the first thing you want to do is find the antiderivative of the function 4x. And that's going to be 4x squared over 2. Now, you don't need to do the plus c. There is no constant that we're going to need to worry about anymore. So definite integrals, you don't need the plus c. Now, that's the antiderivative, and I want to evaluate this from 1 to 3. So this is the notation. Okay. So this is going to be, let's see, by the way, 4 over 2 is just 2. So we get 2x squared. So it's going to be f of b, if I plug 3 into, let's just call this 2x squared from 1 to 3. If I plug in 2 to that, it's going to be 2 times, excuse me, if I plug in, my upper limit's b, if I plug in 3 to that, it's going to be 2 times 3 squared, minus f of a, which is 2 times, x is now 1 squared. This is just the f of b minus f of a. This is f of b minus f of a. And I guess I'll tell you, in this case, f of x would be 2x squared. And then we just need to plug those in and see what we get. So 3 squared is 9. 9 times 2 is 18. 1 squared is 1. 2 times 1 is 2. 18 minus 2 is 16. So this whole thing is equal to 16. And that's it. We just applied the fundamental theorem of calculus there. And this particular function is just a line. We could have thought of this as area and still got 16. The graph of 4x from 1 to 3, let's see, it's going to look something like that. So from 1 to 3, that's the area under this curve, which isn't actually that bad to find. Let's see, when x is 1, this is 4. When x is 3 times 4, this is going to be 12. Let's see, the area of this rectangle down here, the base is 2, the height is 4. 2 times 4 is 8. Here we have a triangle. The area of the triangle is 1/2 base times height. The base is 2. The height, to go from 4 to 12, is 8. Half of 2 is 1, so then 1 times 8 is 8. So 8 and 8, if I add the triangle and the rectangle, I get that the area under this curve is 16 total, which is exactly what we got. Now, maybe using the geometry formula is easier in that case, but if you look at part B, the graph of 3x squared minus 1, that graph is going to be something like that. And if I want to find the area between, -2, wherever -2 is, and 5, this becomes a challenging problem, because there's like this area here, but then this area down here is negative, and this area up here is positive, and there's going to be some like canceling out stuff. So this is a trickier problem, and that's why the fundamental theorem of calculus is going to be a little more helpful. So again, the antiderivative of 3x squared minus 1. Or again, I need to do f of b minus f of a. The antiderivative of that is going to be 3x cubed over 3 minus 1x. Remember, there's no constant here. From -2 to 5. Now the 3's cancel out, so it's just really x cubed minus x. So it's going to be x cubed minus x, and I'm going to plug in, let's plug in 5. This is f of b. I'm putting parentheses here. It's one of those things where the more you do it, the more you'll see it's going to be just very helpful. You'll make a lot less mistakes when you use these big parentheses. So x cubed minus x when I plug in 5, and I need to do x cubed minus x when I plug in -2. Cubed. And we're plugging in -2. So again, this is just f of b minus f of a. All right. So then just throw that in the calculator. 5 cubed is 125, minus 5 is 120. And -2 cubed is -8. -2 is +2, so -8 plus 2 is -6. And then just be careful here. We have a double negative, and that's why the parentheses are going to be helpful. This is really just going to be +6. And 120 plus 6 is 126. So the area between x equals -2, x equals 5, the x-axis, and the function 3x squared minus 1 is 126. Not that I've really used this, but maybe, if you guys want to check your work and stuff, you can plug in antiderivatives and derivatives, definite integrals and actual derivatives, into your calculator if you wanted to. So if I want to do like this one right here, the definite integral of the function 4x from 1 to 3. Just go to the math button, number 9 function interval. And if I want to do, let's see, we're going to go from 1 to 3. The function is 4 times that variable with respect to that variable. Oops, that's not what I want. Okay. And then I should, so that I messed that up because of the DAX. Let me try that one time. So math, you're going to go all the way down to 9. We're going from 1 to 3 of the function 4x dx. And we should get 16. And there it is. So your calculator can do a lot of this stuff for you, especially when the stuff gets really, really difficult. Antiderivatives can be a lot more trickier than derivatives. Here's another example. Evaluate each definite integral. Copy it down. You can try it on your own. The first thing that I would do is just rewrite this as the definite integral of x to the -2 dx, and then just use my power rule. So that's going to be x to the -1 over -1. And we're going to go from 2 to 4. So that's really just going to be, you can float the negative to the numerator, and that's just going to give me, so it's going to be negative, and I can rewrite x to the negative 1 as 1 over x from 2 to 4. So that's going to be negative 1 over 4 minus negative 1 over 2. So again, that's f of b minus f of a. The double negative here is going to make that a plus. And let's see, 1/2 is the same thing as 2/4. So 2/4 minus 1/4 is 1/4. So that answers that question. That's another definite integral, and that's really it. Here's another question. It's worded differently, but it's the same process. Determine the area under the curve of y equals negative x squared plus 4 between x equals negative 1 and 2. So if I was graphing, 4 is, that's going to wind us up above 4. Negative x squared is just going to come down like this. The intercepts are going to be negative 2 and positive 2. So I want to find the area between negative 1 and 2. So that's this area right here. And if I want to find the area under the curve, I can take the definite integral. I'm going from negative 1 to 2 of negative x squared plus 4 dx. And then just use our antiderivative. That's going to be negative x cubed over 3 plus 4x. We're going from negative 1 to 2. Negative 1 to 2. So that's going to be negative, I'm going to call this 1/3 x cubed. So negative 1/3 x cubed minus 4 times x. And x is going from negative 3 to 2. So f of b, we're going to plug in b. Minus f of a, which is going to be negative 1/3 a cubed plus 4 times a. And a is 2. Oh, excuse me, negative 1. So again, that's f of b minus f of a. And let's see what we get. 2 cubed is 8, so that's going to be negative 8/3 minus 4 times 2 is 8. Negative 1 cubed is negative 1. That double negative is going to make that a positive 1/3. And then 4 times negative 1 is negative 4. Let's see. So that's going to end up being 12 minus 3, I guess. I'm just looking at my answer key now, which is 9. What am I missing here? That's a plus. Okay. That should be a plus. That should be a plus. So let's see. 8 is the same thing. So that's 24/3 minus 8/3. Let's see. Let's check this out. 8 times 3 is 24. 24/3, that's 16. And then 1/3 minus 4. Oh, I know what I did. Okay. I was wondering why I was doing this nicely. 8 minus 4 is 4. That's going to be 8 plus, so that's going to be, that negative is going to make that a positive if we distribute the negative. 8 plus 4 is 12. And then negative 8 minus 1/3 is negative 9/3. And negative 9/3, 9 divided by 3 is 3, so we get negative 3. All right, so that was kind of how I did it in my head, by just combining the fractions and combining the whole numbers, and that worked out kind of nicely. Is that it for this video? Okay, so these are just 3 more examples. I want you to kind of try these on your own and check them. I'm going to run through them quickly so you can pause the video and see if you can get them on your own. But you know, just like before, take the antiderivative, plug in our limits of integration, and you're done. So the antiderivative of the first one is going to be 1/3 x cubed minus 3x from 1 to 2, which is going to be, let's see if I plug in 2. 2 cubed is 8, so it's going to be 8 thirds. Minus 3 times 2 is 6. If I plug in 1, that's just going to be 1 third minus 3. And that's going to give us negative 2 thirds. Okay. For part B, I would first rewrite that as the integral of 3x to the 1/2 from 1 to 4, which is going to be 3x to, let's see, to the 3/2 over 3/2 from 1 to 4. Let's see, keep change flip, so that's just going to be the same thing as dividing by 3/2, the same thing as multiplying by 2 thirds, and the 3's will cancel out, so we're just going to get 2x to the 3/2 from 1 to 4. So that's going to be 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Let's see, the 4 to the 3/2. Well, the square root of 4 is 2. 2 cubed is 8, and 8 times 2 is 16. 1 to the 3/2 is 1, so 2 times 1 is 2, so that's going to be minus 2. So 16 minus 2 is 14. And part C, the antiderivative of 0 from 0 to power 4 is secant squared. X dx, I would look up that one in our chart of antiderivatives, and that's just the antiderivative of that is tangent x. So the derivative of tangent x is secant squared, if you remember, from 0 to pi over 4. And tangent of pi over 4 is 1. And tangent of 0 is 0. Equals 1. You could use your unit circle to remember that, right? Tangent of pi over 4, that's the one where it's root 2 over 2, root 2 over 2. And if you divide root 2 over 2 over root 2 over 2, you just get 1. And tangent of 0 would be 0 because tangent sine over cosine, and sine of 0 is 0, so 0 divided by cosine of 0 is going to be 0 divided by 1, which is 0. And we get 1. All right, so that's it for the first part of this section.